I've talked previously about complexity theory and complex systems, and I'm going to talk over the next few videos, I'm not sure exactly how many, about how to study complexity. And the features of complex systems make it particularly difficult to study them. First of all, complex systems are very sensitive to their initial conditions. This is the butterfly effect. A very small change in those initial conditions can lead to very large differences in outcomes. And what I'm going to do today is to have a look at how to study that if every time you set the system running it produces a different output. You'll remember that this has its origins in the work of Lorentz, who was trying to run computer simulations of the weather. And when he put numbers in that were not quite accurate, weather patterns changed completely in his simulation of them. So when we start looking at a system, if we set it up with any kind of error in the inputs, any kind of slight differences in the beginning conditions, it will unfold differently as the time goes on. And that makes it particularly difficult because in one sense anything could happen in a complex system. So we need to look at complex systems not simply once, but we need to look at them time and time again to see which outcomes are likely and which outcomes are unlikely. The second feature of complex systems is that they show similarities at different levels. They have what's called recursive symmetry. I mean, this helps us because it means in one sense we can look for the whole pattern in a part, though the parts of the pattern are often repeated at different levels. But the third feature is there's no strong connection between the behaviour at different levels. There's no causal connection, or there's no derivable. You can't tell always what it's going to do at a greater level of aggregation than it's going to do at a lower level of aggregation because there are emergent properties. And the phenomenon of emergence means that the big scale patterns arise out of the patterns at a lower level, but they're not, strictly speaking, determined by them. And all of those features make the study of complex systems highly suitable for computer simulation. Well, partly, if you think about Lorentz, complexity theory came out of computer simulation, but the advantage of computer simulation is that you can run it again and again and again and look at it to try and see the patterns that are beyond what happens in a single case. You're looking at trying to get a sense of how robust the system is, how likely it is to behave in a particular way when it's run repeatedly. And what I'm going to do today is to look at computer simulation and the simulations that I'm going to be looking at are what are called agent-based models. And the starting point for this, what I'm going to take as my starting point, is the work of Craig Reynolds. Now, Craig Reynolds was working in the 1970s. He was a graphics designer working on computer simulation for movies, and he wanted to simulate a flock of birds. And what he did was to write a computer program, and in the computer program each bird in his program appeared on the screen, and the bird followed some very simple rules. First of all, detected where around it there were other birds. So a fairly local mapping of the birds that were around it, and what it then did was steer towards where most of the neighbouring birds were. It would steer towards the direction where it could see the flock was denser. That's the first rule, a rule of cohesion. It wanted to stay with other birds. The second rule he supposed was that it was going to try not to bump into other birds. When it got very close to birds, it would try and avoid them. And the third simple rule was that it would look or detect, perhaps a computer program doesn't perhaps look, it's anthropomorphizing it to say it looks, but it detects which direction and with what speed the other birds are moving in its area. And it will try and align its movement so that it aligns roughly with the movement of the other birds in its area. Now, these are not strictly speaking birds, they're individual agents, each one independently, and that's why they're agents, independently detects what its neighbours are doing and applies those three simple rules. A rule of cohesion, they move together. A rule of separation, they try not to bump into each other. And a rule of alignment, and that's to try and adjust, to move its motion to line up with the movement of other agents in its immediate area. And the name Craig Reynolds gave to these agents is Boids. The pieces of computer coding that put a dot on a screen to simulate the movement of birds in a flock. And what Reynolds discovered was, which he was looking for, was that from those three simple rules, those agents, the birds will swarm and swirl and swoop like starlings in a murmuration. That was exactly the effect he was looking for, was a computer simulation of the movement of birds for his filmmaking. His profession was filmmaking. But we're going to make use of that same idea now to have a look at the movement of agents in an environment. They're going to take those three simple rules, and we're going to see the Boids moving, and because it's a computer simulation we can run it again and again. In the computer simulation I've got for you, I'm going to start off with 250 Boids, and first of all they're going to be distributed randomly into a space, and they're going to, at random, they're going to be given an initial motion, an initial position, all of those things randomized. And because it's random, because of the it's sensitive to initial conditions, what happens is not exactly predictable. we need to look at it again and again in order to see that working, see the system working, and to try and see what the outcome is going to be when each Boyd has 3 simple rules. And what we're going to get, as Reynolds himself got, was large-scale patterns arising from those simple local rules. But because it's a computer simulation, we can also change the emphasis on those different rules. What happens if we make the force of cohesion stronger or weaker? What happens if we make the force of alignment stronger or weaker? And what happens if we make the force of separation stronger or weaker? And we can look at those patterns and see how robust they are to changes in those initial rules, or the strength with which those initial rules are applied. Now, what I'm doing here is I'm showing you a program that I worked with a friend and colleague in Beijing, Professor Li Chaomin, and she and I have worked on this program. We actually got ChatGPT to write the program for us to our specification, and I'm going to show you now what happens when you put random Boyds together, 250 Boyds in a space with those rules, and set them running. And what you'll see, as I said to you, as Reynolds found, what we get is this swirling motion as the birds, the Boyds, struggle to stay together, to keep going in the similar direction to their immediate neighbours, and not to bump into each other. Naturally, it results in large-scale swirling together. By the way, what I'm going to show you next is that if you turn off the force of alignment, the swirling patterns don't happen. It's important, and I think it's kind of worth commenting on, that the alignment is necessary. Now, the alignment involves looking at the speed and direction of the movement of other Boyds in the pattern. And that means in some way anticipating where they're going to be next. And it's significant to me at the moment that that sense of anticipation, that looking to have some connection to the future, is crucial in producing these unifying patterns. If we just leave the Boyds together with a force of cohesion and a force of separation, we just get a random looking mess of movement that doesn't coalesce into this larger pattern. So, to take away from this lesson, what happens here is that we can develop a computer simulation that shows features of complex systems. We can, with the computer program, we can create an agent-based model. That's one form of complex system. We can run it again and again, and we can start by repeatedly running it, seeing which features depend on which parts of the rules that are controlling the behaviour of the agents. Now, there's not a simple one-to-one relationship. I can't say to you, this particular force is definitely creating this outcome, because this property, the emergent property of complex systems, means that it's not possible to derive exactly from the rules that we've got to know beforehand exactly what patterns the system is going to run into. We only get an overall idea of what sort of patterns occur. By looking at computer simulations of complex systems, we can start to develop ideas about how they function, what's important in them, and which features will repeatedly occur if we run the simulations again and again.